Yeah, I mean, everything you eat, not really meat, but everything else has carbohydrates. It's the hard part of the cell wall is made of it.
Cell membrane.
You're close. Cellulose.
No.
Cellulose, yeah. So like celery, it's like all cellulose. Our body can't really break that down. So you actually use more calories trying to break it down than you get from eating it. Anyways, that's kind of a tangent. But they're still good for you because they have fiber, and there are things you get out of celery. There's nutrients, but just in terms of calories. But one more thing then I'll get off my soapbox. If any of you start at any point in your life eating food and really worrying about the calories, you need to reassess what's going on, because that's not healthy. Healthy is just eating healthy food and being happy with who you are. There, moving on. Catalysts.
And this is my TED Talk.
That'd be cool. TED Talks, sir. Those are great.
You already have a YouTube channel.
It's actually being recorded. There you go. All right. Now, what does a catalyst do? Speeds up a reaction. So, what does a catalyst do? Speeds up a reaction. What's another way to say that?
Increases
reaction rate. Increases reaction rate. Yes, I went on a little rant about that yesterday. Okay. Good. Either word, either phrase is fine with me.
Don't you mean speeds up a reaction?
Whatever. Speeds up. Yeah. I don't know what I was thinking. Good catch. Speeds up a reaction. Okay. How does it speed up a reaction or increase reaction rate?
Lowers the activation.
Yeah, decrease or lower activation energy. Either one. Lowers activation energy. And we all know what activation energy is, except Corey knows better than all of us. Say it.
Can I keep going?
Yep.
The amount of energy to take it. The amount of energy needed to start a reaction.
Yes, very good. We all need to memorize that. All right, good. Lowers activation energy. All right, now, let's talk about what a catalyst does not do. Why? Because there could be a question on this. So, don't write this. This is just reference here. What part of this curve doesn't change because that dotted line is there? The reactants and products don't change.
Heat reaction.
Yeah, delta H does not change. The, here, actually, sorry, don't write that. Catalyst does not, underline does not, change the delta H RXN, meaning if a reaction gives off, like the last one, gives off 91.8 kilojoules, whether you use a catalyst or not, it still gives off 91.8 kilojoules. It just gives off that energy faster. That's it. Does not change the delta H. I'm really trying to make that clear. Why? If we think of the hump here, the curve, the mountain, whatever, as like directions, like on Google Maps or whatever. If this is your home and this is the school, your home doesn't move when you leave, and the school doesn't move either. Those two are like your destinations. Your path can be changed, right? How you get there changes, but the actual locations don't change. That's exactly what I'm talking about, right? So because they don't move, the delta H doesn't move either. All right. What else doesn't it change? You may not be able to answer this.
That was the molecules thing, right? Didn't we talk about something that didn't do something?
Oh, the amount of molecules reacting.
Yeah, okay, yeah. So it actually does not alter the reaction. And what does that mean? In terms of particles. That's still kind of vague. That's not a very good way to write it, I admit. I guess a better way to write it would be the catalyst doesn't take part in the reaction. So it doesn't affect the reaction at all. In other words, if this is N2 plus H2, and this is NH3, that example we just did, the warm-up, whether you add a catalyst or not, it's still nitrogen and hydrogen reacting and making ammonia. The reaction doesn't change. Yes, it reacts faster. It happens faster, but the actual synthesis reaction doesn't change in terms of the particles involved. So catalysts aren't actually reacting. They're not a reactant, they're not a product. Yeah.
Could heat count as a catalyst?
So I'll write this and then you decide. Catalysts can be reused. So now, what do you think? I don't know if that helps you or not.
Well, what do you mean by reuse?
I mean,
Like they
that
can
means
use
he
gas.
can't, because
Just
like,
tell them yes or no, because Quinn and Will go on.
I know they will. That's all right. It's fine. So, if you give a reaction some energy, let's put a number to it. 100 joules of energy, 100 kilojoules of energy. That energy goes into helping this reaction do whatever it does, okay? And then because of the law of conservation of energy, that 100 joule has been transferred to something. So, using that definition, no, heat's not a catalyst because you can't take that same 100 joules and reuse it.
okay.
But I can see why you're saying that. Typically, catalysts are compounds or elements. So, oh, what did I pour into the graduated cylinder?
Dish soap. Well, hydrogen.
Water.
Hydrogen peroxide was the thing now. So,
I mean, you poured both of them.
right, yeah. So hydrogen peroxide decomposes faster when I add a catalyst. The catalyst was iodine, and that iodine is an element, and I couldn't recapture that. But if you did the reaction without the soap, and you had the equipment, and you know we're a better lab technician than me, you could take that iodine back out. Why? Because it's an actual element. So it's heat's different. That's not you know something you can really grab onto and remove. But this is not a huge thing on the reagents. I talk about it because it is part of a catalyst. You have catalysts in your body that help biological processes, and it continues to work over and over. Remember the enzyme substrate with the lock and key method? So the catalyst can grab something, grab an enzyme, stick it in the substrate, and then go do it again. So the catalyst is just kind of the middleman that helps that process happen. As the processes occur, products and reactants can decrease or increase, but the catalyst kind of stays the same. So the analogy I use, it doesn't take part and it can be reused. Best example is a teacher or a coach. All right, so like I coach, I teach, but I'm doing that every year, whether it's you guys or other students or players. So I'm being reused. The players are not, the students are not. So that's, and I'm not taking tests, I'm not playing in the game. So that's a good way to help, you know, understand this. So that's what a catalyst does. It helps, but it doesn't actually take part, and then it can be reused. One last thing here. Cars, trucks, I believe all vehicles have these. It limits the bad stuff that comes out of the exhaust.
Electric cars now.
You're right, Will. I was thinking combust. You're right. No, you're right. Electric cars don't have this because there's no exhaust.
What?
An air filter, something?
It's called the name. This is almost it's in the name of the
Carburetor.
Catalytic.
catalytic converter. Right. It takes out the really nasty hydrocarbons and nitrogen compounds that are in the byproducts of combustion. So all of the junk doesn't come spewing out of the cars. It's bad enough what comes out already, CO2 and other things. But catalytic converter, it's reused. It's not like you have to go get a new catalytic converter every time you start your car. That would not really work out too well. So that's the analogy there. It's this substance that's in the exhaust that when the gas passes through, it essentially kind of like, it's almost like a magnet. It gets sucked to it and then filters through, and then there's better gases that come out the tailpipe. All right. Okay, we are done with that topic. What's that topic? We've been focusing on reaction rate. The term for reaction rate I didn't really spell out for you guys is kinetics. You don't have to write this down, but kinetics is basically the study of how fast reactions are in collisions, collision theory. So that's what we just finished up. Next, we're learning about this. Write this down, equilibrium. How much time do we have? Good. But before I do that, let's just review the main points of kinetics, the reaction rate stuff. In order for a reaction to occur, what must happen?
Correct orientation.
Effective collisions, very good. And one requirement is proper orientation. What else?
So enough energy.
Good. You need enough energy. Sufficient energy. You need enough energy. Good. All right. 4 things you can do to speed up a reaction. Give me one.
Heat it up.
Heat it up.
Add a catalyst.
Add a catalyst.
Increase the surface area.
Increase surface area. Silas, one more. Add a catalyst. Sorry, add a catalyst. Heat it up. What did you say? Increase surface area. Increase concentration. Good. All right. Moving on. Now, equilibrium. When I write that word down and you read it, what do you think?
Equal.
Good. But I don't want you to think equal. We talked about this
Same.
earlier in the year.
It's like the
Close.
The molecules have to be the same to like
Same on both sides.
collision
Close.
Collision theory.
Give me another word instead of equal or same. Think of scales.
Balance.
Matching.
Balance.
Balanced.
Balanced. Write that down. Balanced. There's actually 3 words that you're going to hear a lot of here. Balanced, equal, and constant. Balanced, equal, and constant. They all don't mean the same thing. Balanced, equal, and constant. All right? On a playground. I say balanced, you think? Teeter-totter, seesaw, right. Good. I use that to actually teach this concept. All right, I'm going to use you people. Here, I'll stop recording because I think that's illegal to record students without